In this video, I would like to state the three main conclusions that we get when we look at continuous functions on compact domains. The first one we've already proven, so we will prove the second two. Okay, take a moment to read through this preamble and the three statements, and then I will come back, illustrate a basic example of what's going on, and then we will prove these two statements. If you are a little rusty on the definition of uniform continuity, don't worry, I will bring that into the proof. In the usual way, as much as we can be general, we like to do so. So imagine that f is a continuous function from a compact subset of one metric space to another. One thing that we have already seen is that a continuous function on a compact set has compact image. So f of a is a compact subset of the codomain N. What we are going to look at in this video is that f is uniformly continuous on A. This is a stronger form of continuity, and I will state the definition in a moment. But a continuous function on a compact set is uniformly continuous. That's the kind of thing you want to say to yourself like every day if you're learning this. And then the other statement that I would like to prove in this lecture is what I will call the extreme value theorem, kind of tying it back to calculus and optimization techniques in calculus. So this says that if a function is continuous on a compact domain, then you expect it to attain its infimum and supremum. In other words, it has a minimum output and a maximum output. I've just realized I need to point out to you that when we state this extreme value theorem, we are not assuming that we are mapping to just a general metric space. Here, I'm saying that the codomain is R so that we can order the outputs. Makes sense to say there's a minimum and a maximum. Okay, let me sketch a picture. It's not going to be too exciting of a picture, but I think I can capture basically all three statements at once. So imagine, I'm going to sketch my function first. Okay, so here's the graph of a function from R to R. So the domain is R, and the codomain is R, like this. Statement 1 says that the image of this function over this compact domain, so here my intention is to graph a real valued function of one variable over the closed bounded interval from A to B, which we know to be compact. When I look at its image over in the codomain, what I see is that it's going to also be compact. In fact, in this particular case, it's a closed bounded interval. Okay, so that's statement number 1. The image is compact. This is a compact subset of the codomain R. The second statement is a little harder to see here, but f is uniformly continuous over this compact domain. What that means essentially is that if I want my outputs to be within some distance epsilon of each other, I can pick some measurement in the domain, delta, which works across the domain. That's different than regular continuity, where your choice of delta might depend not only on the epsilon that you select, but also your location in the domain. Uniform continuity kind of removes that location-specific choice of delta. Okay, it's hard to see here that that would have to be the case. Typically, what you want to imagine is something like y equals x squared, which if you plot it forever, if I continued this, it would just maybe get steeper and steeper. Like if you imagine that this function turns steeper and steeper as the domain stretches off to the right, then maybe a delta that works here would not work over here. And if I let my domain go on forever, it's like I could never make one choice of delta that would work as I slid to the right. That's what happens when you look at y equals x squared. However, in this scenario, it's like if my delta will work for these steep parts over this closed bounded domain, it will actually work across the domain. Okay, so that one's hardest to illustrate, but we'll revisit that notion in a moment. And then what we have here is that our function has an actual maximum output and a minimum output. So the minimum is occurring here, and the maximum is actually occurring at B. So f of x1 in my picture, that's supposed to be an x, f of x1 is the minimum of the set f of A, whereas f of B, call it x2, is the overall maximum. Your function attains minimum and maximum values when it's continuous over a compact domain. If you took away b, say I looked at the open interval from a to b, I would still be attaining my minimum. So it's not like it wouldn't ever do that. But if I considered this function over the open interval from a to b, I would never attain this value up here. So that's the usage of the word attain here. I could approach it. B wasn't part of the domain. As I approach b, I might be approaching this value, but I don't get there if b is not part of the domain. So it's like you might have a soup and an infinite soup without landing on them. Here we're saying if the domain is compact, that's not the case. You have minimum and maximum, not just infinite soup. Okay, I think I've talked through this enough. So let's now look at the proof of the second statement. As I was erasing the example I sketched, I decided that I wanted to discuss the behavior a little bit more. So if you stick with me all the way through the end of this video, I will give you a specific function which is not over a compact domain. It is continuous, but not over a compact domain, and we will examine the three properties that we are looking at. So I will have another example at the end of this video, but let's move on to the second statement. We want to show that a continuous function on a compact domain is uniformly continuous. So if you haven't seen it recently, here I've put up the idea of uniform continuity. It sounds a lot like regular continuity, but the key distinction is that the delta that we choose, so this delta expression here, has to work across the entire domain. So I like to think of uniform continuity as a statement not only about the function, but also about the domain. We are going to prove this, and I want to give you a moment to kind of visualize what will happen. It's a little bit of a technical proof, so you might not be able to write down every single detail, but here's the idea. By assumption, f is continuous on the domain A. When we say that, we mean that f is satisfying the definition of continuity at each point in A. So continuity is a point-based notion, whereas uniform continuity is about the entire domain. If f is continuous at every single point in A, then that means that for some choice of epsilon, at each point, I can make the choice of a radius delta defining a neighborhood around each input on which, if you grab another input from that delta neighborhood and compare the outputs, I should probably write this out in a moment because I'm starting to get lost with my neighborhoods, then the outputs would be within distance epsilon of each other. So what I'm trying to get at with this speech that I'm saying out loud and will write down is that every point in the domain is going to admit a useful delta neighborhood. So it's like we can draw a delta neighborhood around each point in the domain. Our domain is compact. So I'm trying to allude to a particular type of construction that we look at when we study compact sets. Take a moment and name that. So what am I doing? What am I saying? And then start to think about like what we will do with that construction and what that might lead to. And then I will come back and write everything down so you don't have to just listen to me say all these notions out loud. The notion that I wanted you to name, the construction I was doing out loud, was that of an open cover of a compact set. We will take that cover and reduce down to a finite subcover. Okay, so that's a preview of where we're going with this proof. It's going to be a direct proof. This is an epsilon delta proof, so our first sentence should be, let epsilon be greater than 0. Now, I've stated out loud what it meant to say that f is continuous on A. Let me write that down. So if I lost you with all the kind of stream of speaking I was doing a moment ago, we are going to write all those ideas down. Since f is continuous on A, for each point in A, so for each x in A, there exists a delta radius based on this x, so that if you're within distance delta of x, your outputs are suitably close measured by epsilon. Okay, saying too much out loud, let's keep writing. For each x in A, there exists a radius which depends on x. So that's how normal continuity works. That's why I'm writing subscript x here. So that whenever Let's see, how do I want to write this? How about Z, another input, is in this delta x neighborhood around this point. So the ball of radius delta x around x. And let me also make sure it's in the domain. So I will write the intersection of that with A just to make sure that we're only evaluating points from the actual domain. It follows that f of z is in the epsilon neighborhood around f of x. I'm actually going to write something a little different because this is going to be a proof with the triangle inequality. We're going to need to insist that we're even closer than epsilon. We're epsilon over 2 distance away from f of x. All right, recapping so far. Because we know that we are looking at a continuous function, the definition of continuity, which is a point-based definition, is holding here. So for every point in the domain, there's a radius for that point, so that whenever the distance from any other input to this point, x, is less than that radius, then the distance from the output, which I'm calling here f of z, to f of x is less than traditionally epsilon. Here, because of a triangle inequality, we will insist that delta x is being chosen so that that distance is less than epsilon over 2. Now, if I take all of these neighborhoods around every point in the domain, it is by construction an open cover of A. Each of these is open. Every point in A is being covered by its own delta x neighborhood, so we have an open cover of A. Then these balls of radius delta x around each x in A is an open cover of A. This is an open cover of A, and it's the right kind of open cover. So it's an open cover based on the fact that f is continuous at each point in the domain A. However, I'm actually going to change it a little bit, and that is because, once again, we have a future triangle inequality argument coming up. So I'm going to take each of these radii and cut it in half. This is still an open cover, so all of these open balls with radii chopped in half, they're still open, they still cover the set A, so this is an open cover of a compact set. Therefore, we can reduce down to a finite subcover. Since A is compact, there exists, I'll write this in shorthand, there exists a finite subcover. And notationally, what I'm going to do is call these center points C1, C2 through C capital N. These are like anchor points for our finite subcover. So B delta C1 over 2 around C1 all the way through the open ball of radius delta C capital N over 2 around Cn. Okay. This is delta Cn divided by 2, not delta Cn over 2. I hope that's clear. Let me clean that up a bit. We have a finite collection of these neighborhoods. Each one is anchored around a point from the domain, and each one has a radius. I would like for you to pause for a moment. There's something we do when we realize that we have this, a finite collection of objects where we have this idea of a radius associated to each one of those objects. So what would be the next step? We have a finite collection of radii. Each one is creating a notion of being suitably close. With that kind of collection, we want to take the minimum. So let delta be the minimum of this finite collection of radii. So delta C1, whatever that is, divided by 2, all the way through the capital N. Because it's a finite set, we know such a minimum exists. So that's why compactness is important here. Okay. What's tricky about this proof and about the definition of uniform continuity is I now need to say whenever any two inputs are within distance delta of each other, their outputs are going to be within distance epsilon of each other. So delta here is the delta that we would like to see work for the definition of uniform continuity. All right, so the next step should be to take any two inputs from the domain within distance delta of each other. So let x1, x2 from the domain A satisfy that the distance between them is less than this delta that we've just created. X1 and x2 are random points from the domain. They are not necessarily center points like this. But since this family of sets covers the domain, x1 lives in one of them. So find ck from the finite subcover so that x1 is in the neighborhood of radius delta ck over 2 around ck. Okay, so this is covering the domain, so one of them must cover x1. The thing is that x1 and x2 are very close to each other, but x2 might not be in this actual neighborhood. Maybe x1 is kind of on the edge and x2 is like in the next door neighbor. However, I want to claim that if x2 is really close to x1 and x1 is really close to ck, then x2 is also close enough to ck. So let's see if we can do that via the triangle inequality. So what is the distance now from x2 to ck? What can we say about it? Notice the distance from the other point, x2, to ck. Well, of course, we have to go through the point we can compare both of these two, which is x1. So this is less than or equal to the distance from x1 to x1 to x2 plus the distance from x1 to ck. The distance from x1 to x2 is less than delta. And the distance from x1 to ck is less than delta ck divided by 2. Delta is also less than or equal to delta ck divided by 2 because delta was the minimum of a set that contained this radius. So this is less than or equal to delta ck over 2 plus delta ck over 2. So the distance from x2 to ck is bounded above by delta ck. Let me sketch a picture. See what marker I should use. Let's do it right here. Let's say that this is ck. I'll start with that perspective. This neighborhood around ck has radius delta ck divided by 2, and that's where x1 is. So let's say x1 is here. And then as I was trying to describe, x2 might not actually be in this neighborhood, maybe it's here. What we are now concluding is that x2 may not be in this very small neighborhood around ck, but it's still in a fairly small neighborhood around ck. In particular, if I go back to the original radius, delta ck, it's in this neighborhood. Okay, there's a lot of division by 2 in this proof. I have like 2 different neighborhoods that we're talking about. So take a moment to pause and just read through this, play around with the ideas a little bit. What I would like for you to have arrived at before you continue the proof is what we can now say about f of x2 versus f of ck. So if I know that x2 is within distance delta ck of ck, what kind of conclusion do I get from that information? Okay, we are just about ready to finish the proof. Let's go on to the next line. We will probably pause in the middle of the computation, but what we would like to now compare are f of x1 and f of x2. We would like for those two outputs to be within distance epsilon of each other. since the inputs were within distance delta of each other. Thus, the row distance, so the distance in the codomain between f of x1 and f of x2. We did all this work to bring in ck because actually we are going to compare these outputs individually to f of ck. So this is less than or equal to the row distance from f of x1 to f of ck plus the distance from f of ck to f of x2. Like that, okay. Both x1 and x2 are within distance delta ck of ck. We explicitly wrote that out on the line above. So the distance from x2 to ck is less than delta ck. We actually have an even stronger statement about x1, but we can back out to delta ck. x1 is within distance delta ck over 2 of ck. So of course it's within distance delta ck of ck. Okay. Why is that good? Well, coming back to kind of how we started this proof, this neighborhood here is what we want to think of as this larger neighborhood, right? So this is like, let me kind of annotate here. Imagine I've got x1, x2, instead of just general z. These are both in the ball of radius delta ck around ck. Okay, so I'm just being a little bit more specific in my description here. By the way that delta ck was chosen for ck, it will now follow that f of x1, if you can read this, f of x2 are within distance epsilon over 2 of f of ck. So it's like we forced x1 to be even closer than we would need so that we could also ensure that x2 is suitably close. Okay, let's finish this proof. This distance is now less than epsilon over 2, as is this one. And therefore, let me write as desired, and then we will draw a little box. What do I mean by as desired? I mean that we've now satisfied the definition of uniform continuity for this function on this domain. So given our choice of epsilon greater than 0, we identified a delta greater than 0. We know it's greater than 0 because it's the minimum of a finite set of positive values. So for this epsilon, we have this delta, satisfying the property that if you take any two inputs from the domain whose distance to each other is less than delta, it follows that the distance between their outputs is less than epsilon. To do this construction, we passed through this finite subcover, but now we can back out and just say if x1 and x2 are within distance delta of each other, f of x1 and f of x2 are within distance epsilon of each other. And that is true for any pair of points in this domain. Therefore, this function is uniformly continuous. Okay, I hope you stuck with me all the way through that. I think it's a fun proof, actually, because we get to use the definition of a compact set, the open covers definition. I think that's very satisfying. Sometimes when we talk about compact sets, it's tempting to pass into sequential compactness, or if you're working in Rn, to use closed and boundedness. So I think it's kind of fun to actually find a situation where using an open cover is the best approach. The next proof that we're going to do is much less work. So this was the big proof of this lesson. Let me step aside now so that you can finish copying this down. And then when we come back, we will prove the extreme value theorem. Let's now prove our third result, which is that a continuous function on a compact set whose codomain is the set of real numbers, the Euclidean real number line, attains its infimum and supremum. In other words, when you look at the set of outputs, there's a minimum value and a maximum value. This result is very useful for optimization, but maybe I'll come back to that when we look at our final example. Let's just go forwards with the proof. This proof will be much faster. By the first result, so let me write by result number 1 that we discussed at the start of today's lesson, that was that a continuous function on a compact set has compact image. we know that f of a is a compact subset of R. But when we studied compactness, we concluded that compact sets are closed and bounded, so f of a is closed and bounded. Bounded, there we go. Since f of a is a bounded subset of the real number line, it has an infimum and supremum. That goes really all the way back to day one of real analysis, that the supremum property tells us that every set which is bounded above has a least upper bound and likewise a greatest lower bound. Anyway, so the infimum and supremum of the set of outputs exist. So let me write the infimum of the set of numbers of the form f of x, where x came from A, and likewise the supremum these values exist. They are real numbers. We need to show that they are in f of a. Well, we've already used the boundedness of f of a. So now we just have to refer to the fact that f of a is closed. It's pretty much immediate, but it depends on how many notions about closed sets and accumulation points you have ready to go. Maybe I will prove the rest of it. So my hesitation there was like, I think this is a result we've already proven, but instead of citing it, let me just go ahead and prove it from scratch. That's what I was deciding right now. If the infimum is not in f of a, so let me do a little contradiction. Then every epsilon neighborhood around it must contain a point of f of a. I'll write that down and then I'll explain why that's the case. The ball of radius epsilon around the infimum, let me write inf of f of a. Take away this, it's not even in f of a. This punctured epsilon neighborhood has non-empty intersection with A. This refers to something which I sometimes call the criterion for supes and imps in the study of real numbers. And that is, if this is the infimum, and it's not in the set, then it must be the case that if I travel any distance to the right, so let's say any distance to the right, I have to scoop up something from this set. Otherwise, this would be a greater lower bound. So if that's not in the set, but it's the greatest lower bound, there better be something from the set in here. Again, otherwise, we would be able to move to the right to a greater lower bound. And then since, this is only one direction that matters because we're looking at being a lower bound, might as well form it into a nice symmetric epsilon neighborhood. Okay, so that again is something I like to call the criterion for supes and imps. But then this means that this is an accumulation point of f of a. F of a is closed, so actually it would have to be in f of a. However, this implies that this infimum is an accumulation point of a closed set. Right, is an AP of f of a. And since f of a is a closed set, it can't not be in the set. It has to be in the set. Okay, and no reason to repeat this for the supremum. It's the exact same story. To be an output means to be the result of doing f of something. So there has to be an x1 in A so that f of x1 is the minimum. It's this infimum value, so it's being attained by our function. It actually belongs to the function outputs. I will write that, but I think at this point we are done. Thus, there exists an x1 in A so that f of x1 is this infimum value, which means it's actually a minimum value. Same for the soup. Okay, so that wraps up this proof. I think it's a lot easier than the proof we just did. So to recap, using a result that we have already shown, a continuous function on a compact set has compact image. We know that f of a is compact. So it's closed and bounded. Since it's bounded, it has an infinite soup. And since it's closed, those belong to the set. That's really the argument kind of condensed down to its key ideas. As I mentioned, I would like to just work through one more example of a function which is continuous over a domain which is not compact. I just want to revisit the three statements that we opened with to kind of show the power of compactness. Go ahead and finish copying this down, and then we will look at least one more example. Let's wrap up by just looking at three very famous functions. How about y equals tangent of x graphed on the open interval from negative pi over 2 to pi over 2? Y equals e to the x graphed from 0 to infinity, the closed interval, including 0. And y equals natural log of x graphed from 0, not including 0, up to and including 1. So we have an interval which is not closed but is bounded, closed but not bounded, and then not closed but also bounded. Notice that all of these functions are continuous on these domains, but none of them have compact image. All of them have an unbounded image. So we do not have compact image. Likewise, we're not going to have an overall maximum or minimum in every case because they are unbounded. So tangent has neither a maximum nor a minimum. It just grows to infinity and shrinks to negative infinity as it approaches its vertical asymptotes. And then e to the x, we know, grows to infinity. Natural log of x goes down to negative infinity as you come from the left. So we don't have any ability to provide maxes and mins over these non-compact domains. As I said, when you have a continuous function over a compact domain and you are doing optimization, whatever the context, then you can feel happy because if you're looking at a continuous function over a compact domain and you're trying to optimize, you will have a maximum and minimum value. Also, these functions are not uniformly continuous. Just take tangent, for example. As we approach the asymptote at pi over 2, our function gets steeper and steeper. So some distance delta that works, at some point in the domain, as you slide it closer and closer to the asymptote, you're going to have to shrink delta because the function outputs are going to be getting stretched steeper and steeper as this function approaches this asymptote. So I'm doing this kind of casually, but hopefully you're following the argument. So none of these functions are uniformly continuous because of this behavior that they all have of turning very steep. And yeah, that's it. So we have non-compact images. They're not uniformly continuous, and you can't identify maxes and mins for each one over each of these non-compact domains. On the other hand, if you are looking at a function which is continuous over a compact domain, you would have compact image, you would have uniform continuity, and if your codomain is the real number line, then you do have an actual maximum and minimum value. So this is one of the reasons why we spent so much time really looking at compact sets, because compact sets are important, particularly in the study of, say, optimizing functions. Okay, thank you for your attention.